end of the day yesterday, and I'd forgotten to bring my Scandium baseball bat. If you look on here, there's a number of things. One, it says THT 100 Scandium alloy. Okay, it was really the Soviets who came up with using scandium. We use titanium in some aluminum alloys as a grain refiner. You get titanium nitrides or titanium borides that form as little precipitates and keeps the grains from getting large, and so you get fine-grained aluminum. But scandium works even better. Who knows why the Soviets used it? They probably had a source of scandium, or they had some expert. In the old days in the Soviet system, all you needed was one very powerful person, scientifically, who had some pet idea, or pet, in this case maybe pet metal, but it also has numbers on there like BPF 1.15, and I think it's ball protection factor or something. Anyway, there's all kinds of different things to evaluate whether the baseball bat is safe, because they actually design it for performance. They claim they don't, okay? But aluminum bats hit further than wood bats, okay? And you can prove it. I did a study for someone once, and it turns out if you want to have the maximum energy and momentum transfer, which is what you want, I learned in freshman physics that you had to have equal mass things hitting each other. If I take two billiard balls which weigh the same and hit them together, you can have the maximum energy and mass transfer on the collision. If you take a tennis ball and roll it against the wall, well, the wall has a lot more mass than the tennis ball. The tennis ball will change its momentum by going in reverse, but you don't impart any momentum to that wall. That wall doesn't really move any substantial amount. So if you have unequal masses, well, it turns out you can do the exact same thing for springs. Okay, remember the force of a spring is minus kx, and the energy of a spring is 1/2 kx squared. If you remember, the energy of velocity and mass is 1/2 mv squared, and the momentum is mv. Well, there's sort of an analogous mathematics here. So what you really want to match is the ball stiffness or spring constant to the spring constant of the aluminum. And so it turns out the Naval Surface Weapons Center in China Lake actually has some fancy high-speed cameras, and the people who make the baseball bats are in Southern California, so they contracted with the Navy. You now can use government labs for things if you pay. And they had them take some pictures of bats hitting balls and stuff at high speed. And it turns out wood is not a good match. If you're an electrical engineer, it's an impedance mismatch. You have different stiffness. If you have the same stiffness, which you can get as you get thinner and thinner on that bat wall, then you can get the ball compressing similar to the amount of deformation of the bat when you hit it. You hit a hard ball with one of those bats, and it actually deflects about 1/2 inch. Okay, the ball also deflects about 1/2 inch. The only problem in all this analysis is the ball has a lot of hysteresis because it's got lots of fiber and other stuff if you cross-section a baseball, and it's got rubber cores and things, and that stuff has a lot of frictional or energy loss. So there's a hysteresis in the ball. There's not much hysteresis in the metal. It's pretty much linear. But they get them thinner and thinner such that they can make them so they have excellent what they call coefficient of restitution for hitting the ball. But the problem is you might get one hit before the bat cracks. It's getting so thin. And in fact, they've gotten them so thin that a lot of these bats only last one season, which is great for the companies, okay? They sell more baseball bats. And it turns out people want performance. There's absolutely no question. They're buying performance. They have all these things like the BPF 1.15, or there's some other numbers on there. The NCAA has actually got some of the stiffest requirements so that you don't have people hitting lots of home runs, but you have a safe system where the balls are not coming off so fast that people can't respond. And that's the safety issue. There have been cases where pitchers have been blinded because the ball came off so fast, hit them in the eye, and they couldn't react. And people have done studies of these things. And it's still very controversial because it's sports, okay? Some people want to have the best performance, and some people are worried about safety. And it's just a big debate. Okay, before I keep going on aluminum, I want to tell you everything you need to know about magnesium welding. Okay, and here it is. Oops, you've seen this too many times. The problem with magnesium, and by the way, here's a bar of magnesium. Beryllium and magnesium actually have about the same density, so if you want to know about beryllium. I wanted to get a piece of beryllium, but they wanted, for a 15 thousandths thick piece of beryllium, 1 inch square, they wanted $1,500, which I didn't want to pay. This is zinc, which is a little bit lighter than steel, but not much. That's magnesium. And I don't have a 1 inch bar, a foot long of aluminum, but there's something similar. So you can feel the density differences. And you can see why people would like to get away from steel structures that are similar to the zinc because of the density, and go to aluminum. But if you compare the aluminum and the magnesium, you can see why they'd really like to go to magnesium. Or if you are in space business and you can afford anything, you can go to beryllium, okay? Because the value of a pound saved in a spacecraft is $20,000 per pound to get payload into orbit. The problem with magnesium is it loves to stress corrosion crack. It just, I mean, it's, you know, magnesium, if you look at that galvanic series that we did in corrosion, you got graphite down here, and the other far extreme for an anodic system is magnesium. It's more anodic than virtually anything else you can name on the periodic table. And so it's going to be anodic to anything else that is anywhere near it. And if you have a conductive material like seawater around, it's not going to be good. The problem is residual stresses, because you have a material that's very susceptible for corrosion. If you have any stress, the environment, humidity in the air will stress corrosion crack magnesium. Okay? So the only thing you can do is get rid of the stress. So the only way we use magnesium is, anybody can think of a use of magnesium and what form it's in? Just think of, what do you know that's made out of magnesium?
They make portions of NASCAR.
Yeah. Yeah, and a NASCAR vehicle is worth how much? About $500,000 to $1 million, right? So you can afford, and you only have to drive it for 500 miles, right? Sort of like a cruise missile, only has to last for an hour and a half. You know, the engine in a cruise missile, you know, limited time life. So NASCAR, but there's actually a lot of people are driving around on magnesium wheels, mag wheels on a car. Turns out most of the mag wheels today are actually aluminum, okay? But in the old days, they were magnesium, and they would start pitting after a year. I mean, they'd put clear coat on them and all this other stuff, and they would still start pitting when they're out of magnesium. So they mostly make them out of aluminum, but they'd love to make them out of magnesium, and they did make them out of magnesium. Helicopters often use cast magnesium parts. Today in automobiles, there's about 15 or 20 pounds of magnesium in an automobile, mostly underneath the dashboard, where it's protected from any road salt or anything like that. So it's basically in the occupant compartment, and it's underneath the dashboard, so if it does start to show white rust, people don't see it. They also use magnesium sheet in some applications. So castings or sheet metal. What about castings? Basically don't have residual stress if you make them properly and mount them properly. You don't have screws adding residual stress when you attach them to things. And sheet metal, we've already talked about, 3/8 of an inch is the worst distortion, but sheet metal is too flexible and doesn't create a lot of residual stress. So we screw sheet metal, or we adhesively bond sheet metal magnesium parts. You don't generally weld magnesium, because you always, even in sheet metal, you'll get some residual stresses around that weld, and you'll get cracks because of stress corrosion cracking. That's the Achilles heel. That's why I think I said magnesium is the metal of the future, and automobiles always has and always will be, unless someone solves the stress corrosion cracking problem. Okay. So that's everything you need to know about magnesium welding. We don't do it. I mean, we can do it, and if you go to the welding handbook, they will tell you how to do it. They just won't tell you how to get rid of the crack that falls behind your arc. Okay. We had talked about aluminum alloys, and we had talked about things like 5083 is now kind of what the Navy's using, but everybody uses for a non-heat treatable aluminum alloy. And we're going to talk about design of aluminum in general, but you can match the strength of the non-heat treatable alloys. Okay, there's nothing particularly special. They get 20 or 25 KSI strength, which is not a high strength, but on a strength to weight ratio, a specific strength, if you divide by the density, it's stronger than steel. Okay, and it's lighter, so you can use it in some special applications. And you started building some all aluminum ships, and you want to, well, actually some of the ships might, well, depends on what they do. Aluminum can have very good corrosion resistance in water environments and even salty water environments. Almost always all your sewage treatment plants are made out of aluminum because they've got better corrosion resistance than carbon steel. And so you can afford the aluminum in sewage treatment. You got all kinds of chlorides and everything else coming through that sewage treatment plant. So you can get 30 or 40 years out of aluminum in certain applications, as long as you don't end up with certain types of corrosion and stress corrosion and things like that. But it's really not really any worse than steel, so far as that goes. The heat treatable alloys, on the other hand, we want to talk about welding, have one Achilles heel for the heat treated alloys, and that is, if I look at the alloys, these are well, these aren't my heat treated alloys. Where are my heat treated alloys? Well, anyway, I'll use this. So this is just some commercial aluminum alloys. 1100 is pure aluminum. The 2000 series is the aluminum copper alloys. 4043 is a welding filler metal mostly. 5083 is non-heat treatable. 6061 and 7000 series, these are all heat treatable. Turns out the heat treatable ones have more alloy content. They have magnesium or silicon or copper. The 2000 series is also heat treatable. Some of these have the titanium or zirconium for grain refinement, similar to the scandium, but scandium is more effective but more expensive so far as that goes. But the problem is, we talked about liquation cracking when you get a liquid up there yesterday, and this is actually 2219. So this is what they used to make the space shuttle great big external expendable tank out of. And the problem is the copper alloy. We talked about liquation cracking in nickel-based alloys, but we have the same thing in aluminum alloys. It's an aluminum copper alloy, and the copper will segregate at the grain boundaries, and it will melt while you're heating up the weld up here, and you can see the cracks just running right through the grain boundaries, which basically turn into a Slurpee, okay, liquid solid solution. The other problem with the heat treatable alloys is if you're welding them in their full strength condition, you can't get 100% joint efficiency. You may only get 60% joint efficiency. So yeah, you can get 40 KSI in 6061 aluminum as opposed to 25 KSI in 5083. But after you weld it, you're down to 25 KSI in the weld, because the weld metal is a non-heat treatable, non-precipitation hardened alloy. So you're not going to do any better in the weld metal than you do with non-heat treatable alloys. So that's a problem. To give you an idea of some of the cracking you get, this comes out of Syndoko's book. The first one is this first one is 6061, where they used 1100 filler metal, and I'll explain why this is a problem. The reason it's a problem is 1100 filler metal is nearly pure aluminum, and the 6061 is highly alloyed as a precipitation hardenable alloy. And if you, I don't think I've got a picture. I don't have a picture of this close by. If you look at the phase diagrams for aluminum, almost all of them start out as some eutectic. This is aluminum magnesium silicon, so it's magnesium and silicon added to the alloy, and this is temperature, this is a phase diagram. We got liquid up here. 1100 aluminum is essentially pure aluminum and has a very narrow freezing range. If you have a highly alloyed weld metal, you can also have a narrow freezing range as you go from liquid down to solid in here. This is your liquid plus solid Slurpee region. If you end up mixing a weld metal and a base metal that one's highly alloyed and the other one's lightly alloyed, you'll have a very wide freezing range. Very wide freezing range means more delta T when you're in this liquid solid region. More delta T in that liquid solid region means more total strain. More total strain means more potential to crack. Okay? So it turns out if you take 6061 and weld it with 1100 aluminum, you're liable to end up with a crack because you've got a wide freezing range. Same problem with the nickel copper alloys. Okay? Just liquation, what we call liquation cracking. This is an example of, actually that's hot tearing officially is the technical term. This is 2219 aluminum copper alloy on the outside, 1100 aluminum on the inside, 1100 filler metal. So I've got here at this interface where I have no crack, I have 1100 to 1100, I have a narrow freezing range, no cracks. Here I have 2024 and I have cracking all the way around. Just make a perfect cracking example. In fact, when I was teaching a undergraduate lab a few years ago and I had to come up with some labs, I had the students weld 2024 aluminum, and it's perfect. You always get cracks. I mean, it's very easy to get cracks. In fact, I'll show you some of the data on that. And then they could take those cracks and they could put them in the scanning electron microscope and they could see dendrites, and it was great. Just not a great thing to weld. So one of the things that you can look at is the freezing range or the composition that causes cracking in a number of different aluminum alloys. So this is aluminum silicon, which is 4000 series, 2000 series. Aluminum mag is 5000 series, and aluminum mag silicon, which is 6000 series aluminum alloys. And you find that the composition of the weld, percent of alloying element, you'll get your maximum cracking at some intermediate level. And that's just this wide freezing range. Highly alloyed, no cracking. Lightly alloyed, no cracking. Wide, intermediate, lots of cracking. So why don't we take 5 minutes, you can go get breakfast. I'm going to turn the camera off. And okay.